तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Last time we were discussing class B power amplifier and how one could get rid of the so called crossover distortion, where the voltage crosses over from negative to positive. The transistors do not conduct until V gamma is reached. So, because of that, particularly when the voltage level is low, you get this crossover distortion. So, this distortion can be reduced by class AB biasing, pre-biasing. So, but there is another way of getting rid of this crossover distortion by using negative feedback. So, today we will discuss how we can get rid of the same crossover distortion by using negative feedback. Now, this is the stage which we had discussed, complementary symmetry output stage, wherein input is given here and output is taken here. This is the output and this is the input. So, until V gamma is reached, this transistor will not conduct, thereafter this will conduct and V naught will be equal to V I. It will conduct as a common collector stage. Until minus V gamma is reached, this will not conduct, thereafter for more negative voltages this transistor will conduct and V naught is going to be equal to V I. So, that output waveform is going to be obtained. Now, how to get rid of crossover distortion using negative feedback? We will use an op amp as a driver stage for this output stage and then connect the op amp in its negative feedback configuration. So, this can be connected in negative feedback configuration either by using inverting stage or a non-inverting stage. Now, I am going to do it using an inverting stage, negative. So, if this is R and this is R, since there is a feedback here, if this is V I, as V I goes positive like this, if there is feedback, this is virtual ground. So, current is V I by R and this current will flow through this and develop a potential minus V I, because the resistances are the same. So, V naught is going to be equal to, in this case, minus V I. Now, let us see what happens really. If the diodes do not conduct, when this voltage is 0, obviously these diodes do not conduct. When the diodes do not conduct, there is no feedback from this, we will call it as V I dash now. There is no feedback from the output of the op amp to the input. If there is no feedback, this is under open loop. So, even if this voltage goes above V I slightly, this will try to go to negative saturation. While trying to go to negative saturation, so this will jump, try to go to negative saturation, but the moment minus V gamma is reached, this transistor will start conducting, and once it conducts, it gives negative feedback, this is maintained at virtual ground, and therefore, this output will be automatically followed at the output of the with the phase difference output of the stage. So, again the moment this voltage comes towards 0, this will come to 0, the feedback is broken, and the moment this goes negative slightly, the output will try to go to positive saturation. So, again there is a jump of V gamma, and thereafter there is negative feedback and it follows. So, this is the kind of output that you get. There is going to be a jump here from plus V gamma to minus V gamma, and thereafter the output will be following the input. This kind of output is what is going to be obtained at V I dash. This is V I dash, and here obviously you will get the neat waveform, right, that is corresponding to positive it will be negative, and for corresponding to negative it will be positive. So, even if this voltage is of the order of hundreds of millivolts peak, even though this is going to be of the order of 0.6 to 0.7, that hundreds of millivolts peak will be superimposed over this in this manner. So, this is what is called pre-distorted drive for this. So, that the output is going to follow the input, okay, as though the negative feedback is all the time there. So, this way we can get rid of crossover distortion very easily. The idea is the op amp under negative feedback will formulate the proper drive for the class B stage such that it will jump at the 0 crossover point, biasing the appropriate transistor so as to receive the signal immediately. So, this kind of characteristic will result in if you plot basically your V naught over V I, there is going to be unity gain with inversion. So, it will be perfectly linear, it is going to be linear here. As far as this is concerned, this is going to be linear after a voltage of. So, this is for V I dash with respect to V I dash, this is for V I. V naught versus V I dash, V naught versus V I. This is going to be plus V gamma, this is going to be minus V gamma. That is, if the gain is infinity, this is the jump. If the gain is very high, there will be a certain slope here, okay, and therefore, this is going to be V gamma divided by A, V gamma by A naught, where A naught is the DC gain, right. So, because at this particular point, okay, this is the characteristic, at this point it is going to be V gamma up and V gamma down, okay, and the voltage here is going to be V gamma by A naught. So, that is the error. So, as you see this just let me say this is V gamma, this is minus V gamma, this is plus V gamma, and these points will be respectively reduced by V gamma by A at this point. So, that means the characteristic will be pretty close. If A naught is infinity, this is going to be V gamma minus V gamma, this will be almost merging with 0 here. So, this will be perfectly linear. So, this kind of reduction of the cut in voltage by V gamma by A naught is possible for this combination of transistor with op amp. This kind of circuit can also be used for rectification, etc. Later on we will see how precision rectification can be achieved also by similar combination of op amp with diode. So, crossover distortion is one factor which is somewhat irritating in the efficient power amplification, that is class B, and since that can be got rid of by either biasing it using class AB mode of operation or negative feedback, that is not going to be any disadvantage. So, now we will go to class C tuned power amplifier. Class A and B are essentially power amplifiers which can be used for wideband applications without any problem. Class C on the other hand is restricted to only tuned power amplification. We will see why such a restriction has been put. Now, obviously, it cannot be used for audio or video power amplification here. It can be used only for specifically for RF power amplification, where for transmitters where power output needed is considerable, okay, and specifically narrow band application. So, what is class C? In class B, we made the transistor, individual transistor operate only for half the time period. The other half is taken care of by other transistor, two transistors made up the full sine wave. Here on the other hand, and of course, the operating current was, quiescent current was 0. Here the operating current still remains 0. Not only that, it is reverse biased, base to emitter junction is reverse biased, so that the conduction angle can be made much less than the 180 degrees that is normally there in class B. In class B also it is less than 180 degree because of cut in voltage. Okay. So, if you apply a reverse bias, it can be made much less than the 180 degree. So, let us see how doing that kind of thing we can achieve better performance. Obviously, in class B we got 78.5% efficiency. We have to see whether class C operation can make it more efficient than that. But we have to now make use of only part of the time of conduction. That means, if let us say for a transistor, the normal current waveform, output current waveform is this, and the peak current let us say is IP, okay, is going to be conducting only for part of the period. Let us say this is the thing and this is, let us say, theta. So, it is going to conduct only for part of the period. This is pi, this is 2 pi, and this is actually omega t we have plotting here, okay, and then this is V, I. So, this period theta, this is actually corresponding to pi by 2. So, this point is going to be pi by 2 minus theta by 2. This point is going to be pi by 2 plus theta by 2. So, this is the way it is going to conduct. Next period, of course, it will bring about the same thing. If such is the repetitive nature of this waveform here, we know that this can be expanded by its Fourier series expansion into a DC, we call it A0 or something like that, and fundamental component with peak A1, second harmonic, third harmonic, like that. So, we can select the wanted component, let us say the fundamental, by putting a band pass filter at the fundamental frequency. So, that all the other harmonics are rejected, only the fundamental component is selected. So, this is the idea behind class C tuned power amplifier. Tuned means it is a resonant circuit at the output made up of a tank circuit, so called tank circuit. We can store energy. So, L and C connected in parallel, and effectively the load comes across L and C. So, it is L, C and R. So, essentially it is going to be a tuned circuit L, C and R. This R may be the resultant effect of the load, the antenna load on the primary side of this coil, okay, and this is coupled by means of a coil, so that the maximum power, okay, developed at this point is transferred to the load, that is antenna. So, that is why you have a sort of transformer coil kind of arrangement here. So, that these are all tuned power amplifiers. In all these tuned power amplifiers, maximum power transfer both at the input as well as the output is done, so that it is able to give you maximum available power gain. The active device is able to give you maximum available power gain, okay, as far as the from the source to the load is concerned. So, this is normally what is going to happen. If there is a load, that effect also is going to come as a shunt resistance across this. This will be the output resistance of the device under consideration, and the capacitive leakage resistance and coil resistance all put together. So, essentially we have a current drive here, and this is connected to, let us say, the supply voltage VCC, and we have the device simply connected like this with maybe a reverse bias here minus VBB appropriately, and actually VI, so that this is going to be a combination of the reverse bias and VI, and the moment it conducts, there is going to be a current injected here, signal current injected, which is essentially made to flow into the transistor base, and base current times beta is the collector current. It is going to therefore conduct only during part of the time. So, therefore, if VI is sinusoid, the base current waveform is going to be sinusoid, and therefore, we are perfectly justified in assuming linear relationship between the base current and the collector current. So, beta times base current is also going to be part sinusoid. Okay. So, this much is the way how biasing is done for class C operation, tuned amplifier, okay, tuned here. Class C means it is this, that is biasing. Now, we have to understand how much is the input power. That is very easy. VCC is going to be the supply voltage, DC supply voltage to this, and therefore, through this an average current flows, and that average current corresponds to the average of this particular waveform, this current waveform. So, that therefore, is nothing but VCC into I average is the power input. We are of course neglecting the effect of the input to the transistor itself, because when transistor conducts, there is certain amount of power inputted to the transistor, that is not taken into consideration here, okay, because we are assuming that the most of the power input comes from this supply. That is justified because the current of operation is much higher, beta times higher than the current of operation here. So, this is negligible. Okay. So, VCC into I average is going to be the input power. How to find out I average? I average is nothing but 1 over 2 pi of this waveform, whatever waveform. This waveform exists only from pi by 2 minus theta by 2 to pi by 2 plus theta by 2. Rest of the point it is 0. So, we can integrate, okay, from pi by 2 okay, minus theta by 2 to pi by 2 plus theta by 2. In fact, we do not have to integrate all the way, because we can just integrate for this and double the area. So, I will do that. So, we can integrate up to pi by 2 okay, and say it is double the area. So, this is what we are going to integrate now. So, this waveform is nothing but I sin omega t, this whole thing is I p sin omega t, this is I p sin omega t, minus whatever value is there for this at that point, that has to be subtracted. Okay. So, that corresponds to I p, okay. This value is sin pi by 2 minus theta by 2. Which is cos theta by 2. So, this value is simply cos theta by 2. So, essentially therefore, this is the integration. Is that clear? So, this is nothing but I p by pi, this I p divided by pi into integral of sin omega t is minus cos omega t minus omega t cos theta by 2. The limit from, let us say, pi by 2 minus theta by 2 to pi by 2. So, this is the average. So, this is equal to I p by pi minus cos pi by 2 0 minus pi by 2 cos theta by 2, then the other limit which is minus okay, minus this. So, here it will become plus, both will become plus, and therefore, plus cos omega t cos pi by 2 minus theta by 2, which is sin theta by 2, cos pi by 2 minus theta by 2, which is sin theta by 2, that is over, plus pi by 2 minus theta by 2 cos theta by 2. So, we get pi by 2 cos theta by 2 minus sin, pi by 2 cos theta by 2 plus sin. So, those two get cancelled. So, the answer is this is equal to P I average, therefore, is equal to I p, this is I average, by pi into sin theta by 2 minus theta by 2 cos theta by 2. This is I average, that means P input, power input, which is nothing but VCC into I average, therefore, equals VCC IP by pi okay, sin theta by 2 minus theta by 2 cos theta by 2. We can check this by putting theta equal to pi. By putting theta equal to pi, in fact, there was a minus sine which is already taken. So, theta equal to pi, you will get sine pi by 2 which is 1, pi by 2 cos pi by 2 0. So, this is 1. So, average is I p divided by pi. For a half wave rectified waveform with peak voltage equal to I p, the average is I p by pi, we know. Okay. So, for theta equal to pi, it is satisfied. So, P I is this. Now, we would like to find out the power dissipated during that time. You look at it. This is the time during which there is a current pulse by the transistor. This is the time during which the transistor is conducting. Now, we can clearly say that when it is not conducting, the potential here is going to be VCC. Okay. This is a coil here. So, the potential here is going to be VCC, no current is there. So, if you now plot the voltage VCE as a function of time, it will start at this point with VCC because there is no current all the way up to this point, all the way up to this point. Thereafter, this current pulse is going to generate only voltage waveform corresponding to fundamental. So, the voltage that is going to be generated across the tuned circuit is going to be some Vp sin omega t. The Vp can reach as much as, since this is starting with VCC, almost VCC itself, the peak voltage. It is capable of generating that much value of the peak voltage. So, we will assume that it is almost VCC itself, the peak voltage. Rest of the harmonics are not capable of generating any voltage because LC circuits actually suppresses all the harmonics. Therefore, we will have a voltage which is VCC minus Vp sin omega t, which is VCC sin omega t. That means actually if you assume that this is almost nearly sinusoidal, this is going to be a waveform which is going to be sinusoidal this way all the way up to this, and since it is not going to be of interest for us as far as the rest of the angle is concerned, this waveform is going to be of no concern to us, this portion of the waveform of the voltage. So, it is this that is of interest to us, instantaneous value of voltage waveform, okay, during the time the tube or the transistor is conducting. So, this instantaneous value of current into this instantaneous value of the voltage will give you the instantaneous power. That means, VCC minus, actually speaking it is Vp, which is assumed to be VCC itself, sin omega t. This is the voltage waveform here, that into the current waveform which we already defined as Ip into sin omega t minus cos theta by 2. This has been already defined. This into d omega t is the energy that is stored, okay, the energy dissipated in the transistor during the time period pi by 2 to pi by 2 plus theta by 2. And again we can say that the limit is, because these are symmetric around this pi by 2, we will put the limit instead of pi by 2 plus theta by 2, just pi by 2, and that will be twice the area, twice that divided by 2 pi is the average power that is dissipated. So, power inputted, which has already been evaluated by us, minus power dissipated is the output power. Okay. So, efficiency therefore is nothing but output power divided by input power. We can once again evaluate this. So, if you work out this integral, it will come out to be VCC IP by pi into sin theta by 2, okay, minus theta by 2 cos theta by 2 plus sin theta by 4 minus theta by 4. So, this is the power dissipated in the transistor, average power dissipated in the transistor. So, this will be very helpful for you to find out what the transistor rating should be. Okay. Now, what we are interested in is power output. Power input minus power dissipated is power output, and we already have obtained the power input. Power input we had earlier obtained is nothing but VCC into I average, okay, which is VCC IP by pi into sin theta by 2 minus theta by 2 cos theta by 2. This is going to be the power that is inputted. So, we have to subtract this power dissipated, okay, from the power inputted. You can see this power dissipated at VCC IP by pi sin theta by 2 minus theta by 2 cos theta by 2, which is nothing but the power inputted. Okay. So, this portion is nothing but the power inputted. So, power dissipated is going to be subtracted from power inputted. Okay. So, this has to be subtracted from, so subtract this from power inputted. So, P I minus P D is P naught. So, we will put this VCC IP by pi into sin theta by 2 minus theta by 2 cos theta by 2. This is nothing but power inputted. Okay. Now, the extra thing is plus sin theta by 4 minus theta by 4. This is the extra thing. So, you will see that power output is going to be nothing but, this gets cancelled here, this gets cancelled here, right. So, output power is going to be VCC IP by pi, same thing, into theta by 4 minus sin theta by 4, simple expression. So, or 4 you can take out, 4 pi into theta minus sin theta. So, this is the output power. So, now we are ready for the efficiency, which is output power by input power. So, the efficiency equals output power by input power, output power being VCC IP by 4 into theta minus sin theta divided by input power, which is VCC IP divided by pi into sin theta by 2 cos theta by 2. So, VCC by IP, it is therefore independent of that, VCC by, that is pi by 4, okay, theta minus, I think pi also gets cancelled, 1 by 4. In fact, it is in both the things VCC by IP, VCC IP by pi. Okay. In one it is by 4. So, only 4 will be there. theta minus sin theta by, just verify this, right. At theta equal to pi, this should be the same 78.5. So, theta equal to pi, this is pi sin pi 0. So, this is pi by 4 sin pi by 2 1 cos pi by 2 0. So, it is pi by 4, okay, which is 3.14 by 4. Okay. So, it is correct expression. Therefore, you can see that efficiency is going to be, let us see, because it should be higher than 78.5 for less than pi. Okay. Now, for theta very small, we can make approximations. Theta very small, sin theta is theta minus theta cubed divided by 3 factorial. Okay, rest of the things you can ignore. Okay. Sin theta by 2 is going to be theta by 2, okay, minus theta cubed by 8 into 6. Okay. And cos theta by 2 is equal to 1 minus, okay, the angle squared divided by 2 factorial. So, theta squared by 4 into 2, right. 1 minus, right. Okay. The theta has to be always such that it is 1 minus, okay. It should be less than 1. Okay. So, theta squared by 4 divided by 2. So, now we can substitute these things. So, this for theta small, this is 1 by 4 theta minus sin theta, okay, is going to be theta cubed by 6. Theta minus sin theta, theta theta get cancelled, theta cubed by 6. Then in the denominator sin theta by 2, which is theta by 2 minus theta cubed by 48, right, theta cubed by 48, right. Then minus theta by 2, that is remaining as such, okay, into cos theta by 2, which is 1 minus theta squared by 8, right. So, once again you have theta by 2 getting cancelled with theta by 2, right. So, this is equal to theta cubed by 6 divided by minus theta cubed by 48 plus theta cubed by 16, which is nothing but 48, okay, into 3, right. This is 1 by 16, okay. So, it is 2 by 48, okay, this whole thing divided by 4, okay. So, this comes out to be 1, right. 3 by 48 minus 1 by 48 is 2 by 48, okay, which is how much is it? 1 by 24 is 1 by 6, theta cubed by 6, theta cubed by 6, 100% efficiency. This is the theoretical efficiency. Of course, this is not possible because you cannot make theta equal to 0, because certain amount of power has to be given, okay. Theta has to be non-zero, and therefore, it cannot be 100%, it is always less than 100%, because theta cannot be made equal to 0. Theta going towards 0, okay, efficiency is very nearly equal to 100%. So, it is going to decrease from 100% up to 78.5 for theta equal to 5. Okay. So, this is 100%. Now, this is the maximum ever possible efficiency under the assumption that we have swung almost up to the minimum which is 0, etc., and therefore, these are all not valid, and therefore, efficiency is typically of the order of 70 to 80% for a practical class C power amplifier, which is going to deliver a useful power of about 200 watts. Okay. We can use currents of the order of 10 to 15 amperes, okay, working at about something like 50 to 60 volts, okay, the transistor stages. We can get output power of the order of 100 to 200 watts. Now that we have understood how class C power amplifier works, let us illustrate it by an example. Design a class C power amplifier. This is a typical design tuned to FM transmitter frequency 108 megahertz using 28 volts typical supply used for this transistor power stages supply and power transistor SD1460. Specifications for SD1460: surge current 65 to 70 amperes. This is just one time surge current, okay, which might flow because of sudden change in the voltage or something like that. So, IC max is equal to 16 amperes. So, what is important here is the supply voltage and IC max in our design. Let us see. We just said this shall be a transistor with a tuned circuit this might really go to the antenna like that. So, we have here now an arrangement, let us say, to bias it so that it will work with certain amount of conduction angle. So, effectively we said there is going to be a current pulse here, angle of conduction being decided by us. Smaller the angle of conduction, better is the efficiency. Of course, the output power delivered depends upon the angle of conduction. If you want to deliver large output power, okay, it has to conduct for a longer duration, right. So, let us now see the design, how this is going to work. I max is chosen from this IC max, the collector current 16 amperes. So, we will let us select something like 10 amperes as the permissible maximum current we will have for the transistor typical operation. So, I therefore, the current waveform, okay, shall have 10 amperes as the maximum current in it. It is part of a sine wave. So, we would like to know what the peak amplitude of the current is, of which this is a part. So, I is equal to I p sin omega t minus cos theta by 2 is the definition of the time waveform of the current, okay. And therefore, maximum occurs at this point, it is I p, this is happening when this is equal to 1 minus cos theta by 2 is equal to 10 amperes, that is fixed. So, I p will be 10 by 1 minus cos. Now, theta is to be fixed. Let us take a theta typical angle of 120 degrees. This is for ease of calculation only, for demonstration we are doing. This is around typically 120 degrees. So, cos theta by 2 is cos 60, which is sin 30, which is half. So, 10 by 0.5, which is 20 amperes. What it means is this is a part of a sine wave whose peak current is 20 amperes. Okay. So, you can define this current waveform as 20 sin omega t minus half. Okay. That is the definition of this waveform, 20 sin omega t minus half. This is the definition of the waveform. So, it has a peak current of 10 amperes. Okay. So, the current waveform is well defined now. Now, as far as the transistor is concerned, the voltage specification using 28 volt supply, 28 VCC into IP divided by 4 pi theta minus sin theta is the output power as derived by us last time. So, this is 28, this is 20 as calculated now by 4 pi into theta being 120, which is 2 pi divided by 3 minus sin, okay, of 120. Calculating this, you will get it as 1.227. This is the calculation, 2.093 minus 0.866, 1.227. This is really the output power, which is 28 into 20 by pi into 0.307 for 1.227 by 4, which is approximately 56 watts. Okay. So, this is the output power, 56 watts. Now, the input power, let us find out. VCC IP by pi into sin theta by 2 minus theta by 2 cos theta by 2 is defined as the input power, which is 28 into 20 by pi into sin theta by 2 is sin 60, okay, into theta by 2, theta being 2 pi by 3. So, 2 pi by 6 into cos theta by 2 is half. Okay. So, pi by 6 you get there, the evaluation of which will give you 28 into 20 by pi into 0.343, this factor. Okay. So, if you now take the ratio efficiency, okay, this being common in these two, okay, output power by input power, these will get cancelled, you will get the 0.307 divided by 0.343, which is about 0.895, or efficiency is almost nearly 90%, okay, 89.5%. This is the other answer. In the design, output power is 56 watts, efficiency is nearly 90%, that is 10% of the power is only wasted in the device. Okay. So, once you have this efficiency, the input power is going to be output power, okay, divided by the efficiency, right. So, which is very nearly 56 watts divided by 0.9. I am approximating, okay, 0.895 as 0.9. This is how much? What? 63 watts. Yes, 63 watts. Pardon? Yeah. So, 63 watts is the input power. That means, actually power dissipated, which is also an important thing in the transistor, is going to be 63 watts minus 56 watts, which is going to be about 7 watts. Yes. So, this is the power dissipated in the transistor, average power dissipated in the transistor. Peak power is going to be more than this, right. So, average power dissipated in the transistor is 7 watts. That means, the transistor that is used should be capable of dissipating this kind of average power. Okay. And as far as the average current is concerned, that is going to be what is that value? 63 divided by what is that? 28 volts, which is 2.25 okay, amperes. So, this is the average current okay, supplied by the battery. Okay. So, this completes in sense the complete design of the output stage of our transistor power amplifier. The input stage, please remember, you have to now design this value of VBB and this value of VI R1 R2 in such a manner that this kind of current waveform is coming. 10 amperes divided by beta, let us take typical value of beta, that shall be the peak current of the current waveform that is occurring in the base. Okay. So, the base current is going to be like this, conducting for 120 degrees with 20 that is 10 amperes divided by the beta. Let us say it is typically maybe 50 or so. Okay. So, about 0.2 amperes. Okay. That shall be the current waveform. That current waveform you have to generate using a specific value of VBB and a specific value of peak voltage here with a specific resistance. You have to assume that the transistor conducts okay, for about say 1 volt. V gamma for all these power amplifiers you can typically take as 1 volts as against 0.6 or 0.7, because it is operating at fairly high current. Okay. So, if you take it as about 1 volt, then above 1 volt when it conducts you assume that it is a battery, that means the entire current which is VI by R1 will be pumped into the transistor. Okay. So, you have to assume that this part of the waveform is going to be generated by a sine wave drive here with specific value of Vp. So, that Vp minus 1 divided by R1 is going to be your 0.2 amperes.